Welcome to Effective IAM, Chapter 2, Control Access to Any Resource in AWS, read by the author, Stephen Kuenzli. Let's learn how to control access to any resource in AWS. That's a tall order, so we'll work through a simple example that introduces the key IAM concepts you'll need to be effective. We'll start with the basic IAM access control flow and elements of IAM policies. These security policy elements control a principal's ability to execute an API action that affects a resource, like a bucket. This diagram depicts a simplified access control flow for an AWS API request. First, an application or person authenticates as an IAM role or user principal. A principal is an entity authenticated by AWS and assigned privileges to use within AWS. Then that principal requests an AWS API action, like S3 get object. The AWS Identity and Access Management System, IAM, evaluates that request to determine if it is allowed. IAM does that by evaluating any identity policies attached to the principal, resource policies attached to the resource, for example, an S3 bucket, and service control policies attached to the account. There's other policies too that we'll talk about in a minute. Finally, IAM renders a decision either allowing the request to proceed to the target service API or responds with access denied. At its core, AWS IAM enables you to state whether a principal should be allowed or denied the ability to invoke an API action on a resource. Each of these emphasized terms are key elements of an IAM security policy statement. A policy statement describes which access control rules apply in a given situation. Statements are collected into an IAM security policy document represented as JSON in this form. Each policy document has a version and a statement member element. The version member defines which version of the AWS security policy language the document is written in. Use the latest version, which is 2012-10-17. The statement member contains a list of one or more statement objects. Each statement object has the following form. First, SID. SID, a string identifying the statement's purpose. Effect, this is required. Whether to allow or deny access if the statement applies. Deny always wins when multiple statements apply. Principal, required. Which principles the statement applies to. Most importantly and commonly, an AWS principal. The AWS security policy language supports several kinds of principals. AWS, an AWS account, or IAM user or role principals within an account. May be specified as a single string or list of strings. Usually specifies an IAM entity within your AWS account, your organization, or a partner's account. A service. The name of an AWS service such as cloudtrail.amazonaws.com. Federated, a principal from a federated identity provider such as a corporate IDP integrated via SAML or a public IDP such as Cognito, Google, Facebook, or Amazon. Anonymous, allow anyone access via star. This can be narrowed via conditions. The next element is action, which is required. One or more AWS API actions, the statement will allow or deny the principal to invoke as a string or list of strings. It supports wildcards. Resource. Required. One or more resources the statement applies to, specified as ARNs. Supports wildcards. Condition. Optional. One or more conditions that qualify when the statement applies using context from the request to verify a request was made in a certain way, such as to an encrypted endpoint. The principal, action, and resource each have a negated form that can be used instead of the positive form. These are not principal, not action, and not resource. The negated forms are primarily useful for advanced use cases, such as granting limited access to an AWS service principal, but are difficult to use correctly. Not principal is especially dangerous as it's easy to match nearly every AWS account. So is not resource combined with allow, which makes it trivial to accidentally allow access to all buckets except one. Avoid not principal and not resource. While principal, action, and resource, or their negative form, are required elements, AWS IAM infers the principal for a policy when attached to an IAM user or role. All AWS security policy documents take the form above. Consult the AWS IAM reference guide for the full IAM policy language grammar. AWS supports 5 types of policy, each applying to a different scope. Policy type, scope attachment point, supported effects, and purpose. First, service control policy is attached to an AWS organizational unit or account. It supports deny. Its purpose is to limit an entire AWS organizational unit or account's use of AWS Service API actions. Policy type identity policy attaches to IAM user or role. It supports the effects allow and deny, and its purpose is to grant or limit a principal's use of AWS Service API actions and resources within the account. Policy type permissions boundary attaches to IAM users or roles. It limits allows, and its purpose is to limit an AWS IAM principal's use of AWS Service API actions granted via identity policies, particularly AWS managed policies. Policy type session policy attaches to a security token service session. It supports limiting allows. Its purpose is to limit an IAM role's use of AWS Service API actions granted via identity policies within a given security token service session to those allowed by the session policy. Resource policy attaches to the resource. It supports allow and deny. Its purpose is to grant or limit a principal's use of AWS Service API actions to a particular resource. Resource policies let you grant permissions to other AWS accounts or services on a per-resource basis, enabling cross-account and public access scenarios. Take a moment to think about the level of control and flexibility this language provides. This makes the IAM security policy language very powerful, but also difficult to understand. We'll dive into that later in Chapter 3. Now let's see how these policy elements work in practice by controlling access to an S3 bucket. Now let's control access to an S3 bucket. Let's start with a common deployment scenario and policy requirements. Suppose we have a simple application deployed entirely in AWS. We may have some administrators, customer service outside of AWS, continuous integration delivery as well. But within AWS, we have a Lambda application, a bucket, and roles and users. The application deploys to AWS using an automated delivery pipeline. It runs on AWS Lambda using the app role, is supported by a customer service team, and stores data in the sensitive app data bucket. The deployment must implement the organization's high-level security policy requirements. Implement least privilege, allowing only explicitly specified principals the actions and access to data they need to perform their business function, and denying access to all other principals. Also, require encryption at rest and in transport. Many people approach this by creating an identity policy for the application's IAM role, so let's start there. We can create an identity policy for the app role that grants read and write access to the sensitive app data bucket. It looks like this identity policy, Jason. Once attached to the app role, this identity policy will allow the application to read and write in the sensitive app data bucket. This allow restricted read data statement allows S3 list bucket, S3 get object version, and S3 get object to both the bucket and the objects in the bucket. The allow restricted write data statement allows putting objects and aborting multi-part upload to both the bucket and the objects in the bucket. Once attached to the app role, this identity policy will allow the application to read and write data in the sensitive app data bucket. But problems are lurking. This identity policy grants access to the app role in a minimal way, but it doesn't achieve the full mission of protecting the sensitive application data. What if the app role has another identity policy attached that allows it to delete objects in any bucket? Or other IAM users and roles have the ability to read objects from any S3 bucket in the account. These scenarios are very common. Many identity policies include statements that do not limit the resources they apply to with wildcards either. These scenarios are very common. Many identity policies include statements that do not limit the resources they apply to with wildcards. Either a resource with a star, which matches all resources in the account, or resource with all S3 buckets. This is the case when using AWS managed policies like read-only access or administrator access. AWS managed policies always use resource star since they must be usable in any customer's account. Depending on the use case, wildcards are useful, necessary, and dangerous. Carefully analyze the scope of resources the wildcard matches now and what it could match in the future as resources change. Then decide if the match scope is appropriate. We've just seen that we can allow access to sensitive data with an identity policy, but we can't deny unintended resource access with identity policies in a scalable and maintainable way. It's impractical for engineers to continually be aware of and evaluate every policy for every identity in an account. It's really impractical to update identity policies every time a new resource needs to be protected. So how will we implement the least privilege and encryption requirements for our sensitive data? We need to block unauthorized and insecure access to sensitive data with a different approach: resource policies. Section: Actually implement least privilege. Let's turn the problem around. Deny unauthorized and insecure access to the sensitive data using a resource policy attached to the bucket. This flowchart shows how AWS IAM evaluates policies. Figure 2.3, AWS Policy Evaluation Logic. The decision starts with deny. AWS IAM evaluates all applicable policies and looks, are there any explicit denies? If yes, then we go straight to deny. If no, IAM examines whether a service control policy allows the action if the service control policy exists. If yes, IAM proceeds along to the resource policy. If a resource policy exists and allows the action, then the action is allowed. If not, IAM proceeds to check if there's a permissions boundary attached to the IAM user or role. If there is a permissions boundary and the permissions boundary allows the action, then IAM proceeds to check if there's a session policy. If there's a session policy and it allows, then IAM proceeds to the identity policy. If permissions boundary and session policy don't exist, then that step is skipped. Finally, we are at the identity policy. If the identity policy allows the action, then we proceed to the allow. Otherwise, IAM defaults to denying the action. Whoa, that's a lot. That's the high-level process AWS uses to evaluate security policies and decide, can the caller execute this API action? Any allow in the policy evaluation chain provides access to the resource unless there is an explicit deny. Notice that both identity and resource policies may allow an action. Effects are calculated with this precedence. Explicit deny by matching statement overrides allow. Explicit allow by matching statement, and then an implicit deny when no statement matches. Resource policies apply security rules directly to a resource like an S3 bucket or KMS key. In practice, there are relatively few sensitive data resources in an account. So a more practical approach to protecting the sensitive data is to attach a resource policy that enforces least privilege and best practice. Begin creating a resource policy by identifying precisely who needs access to the bucket and what kind of access they need. Suppose interviews with the application delivery and customer support team reveal the following access requirements for IAM principles. CI user needs administration capabilities to deploy application updates. The admin role needs administration capabilities to fix urgent problems. The app role needs read and write data capabilities for the application to function. And the cust service role needs to read data capabilities to investigate problems. All of these identities and application resources exist within a single account, 111. Now we have enough information to provision the intended access in the steps that follow. Section: Deny, deny, deny. Start by creating a policy with a deny everyone else statement that blocks access from all principals who do not need access to the bucket. Here we have a statement ID, deny everyone else. The effect is deny. The action covers S3:*, so all S3 actions. And it applies to the resource sensitive app data bucket and all of the objects within that bucket. The statement applies to the principal AWS 111, which is the account, the entire account. Now, there's a condition, ARN not equals, with an array in the AWS principal ARN context key. So this identifies 4 principals. admin role, app role, CI user, and cust service role. So those principals will be excluded from this deny. The deny everyone else statement jumps right into the deep end of the IAM policy concepts. The statement denies all principals in account 111 the ability to invoke any S3 API actions on this bucket whenever the condition is met. That condition is when the requester's IAM principal ARN is not one of the intended principals, admin, app, CI, or cust service. This statement narrows the scope of who can access the bucket to these four principals, no matter what their identity policies allow. Remember, explicit deny takes precedence over explicit allow in AWS IAM. We also want to enforce the organization's encryption policy. Require encryption and transport with a deny and secure communication statement. Deny and secure communications. Effect deny. Action S3 star. Resource app sensitive app data /star sensitive app data bucket. Principal. All principals. All AWS principals. Condition. The Boolean request context key AWS secure transport is false. This denies all principals the ability to invoke an S3 API action using an insecure transport. This forces clients to use HTTPS. The AWS API will deny any request made with HTTP when it reaches the AWS API endpoint. Enforce encryption at rest with these deny unencrypted storage and deny storage without KMS encryption statements. Deny unencrypted storage applies the effect of deny to the action S3 put object, to the resource ARN AWS S3 sensitive app data objects, to all principals, where in the request context, the S3 Amazon XAMZ server-side encryption Boolean, the XAMZ server-side encryption key is null. Similarly, in the deny storage without KMS encryption statement, we verify in a condition that, we deny all put object requests if the request context keys do not include a server-side encryption context key of AWS KMS. These statements force clients to do two things. First, all S3 put object operations must use AWS's server-side encryption services on every put. Second, the encryption must use an encryption key managed by the AWS Key Management Service, KMS. We'll discuss these choices in more detail later. For now, know they enforce encryption at rest with a service you can also use to enforce fine-grained data access controls, KMS. Section allow. Now, let's explicitly grant the access each of these principals need with an appropriate statement. Organize the allow statements by needed access capability, not principal. Organizing by access capability simplifies understanding what API actions principals may and may not perform on their resource. You will always know where to look to see if, for example, a principal is allowed to write data. Grant an access capability with a statement using this form. Allow, bracket, capability name, close bracket. Effect allow actions, some list of actions for that capabilities, resource, the bucket and the bucket objects, the principal, AWS star, the condition, ARN equals, and a context key of AWS principal and the identities, a list of the identities that you want to allow. The statement ID describes the statement. The statement ID describes that the statement allows a particular capability such as reading data or administering resources. The resource element applies to all objects in the bucket, such as ARN, AWS S3, sensitive app data /star, and the bucket itself, ARN, AWS S3, sensitive app data. Buckets and bucket objects are distinct resource types. This is an important detail. Access to a bucket is identified and evaluated separately from the objects inside it. Most AWS API actions apply to a single resource type, though some API actions interact with multiple. The principal matches all AWS IAM principals in the AWS principal ARN array. A common policy mistake is to mismatch the API action and covered resource type. Allowing S3 put object to ARN AWS S3 sensitive app data is an example of this mistake. AWS may save the policy depending on what else is in it, but when you actually invoke S3 put object, the operation will fail. The action allowed puts to ARN AWS S3 sensitive app data, a bucket type. But S3 put object operates against objects. Section. Allow writes. The correct allow statement looks like this, which allows writes into the bucket. SID allow restricted write data, effect allow, action, S3 put object, S3 abort multi-part upload, resource. ARN AWS S3 sensitive app data /star, principal, AWS star, condition, ARN equals, AWS principal ARN context key, ARN AWS IAM 111 role /app. This statement allows the app role to put objects and also abort object uploads that are in progress. Allow restricted write data's resource element was narrowed to cover only objects in the bucket because the API actions pertain only to objects. The AWS API docs document which resource types each action works with. Section. Allow administration. Now allow the CI and admin principals to administer the bucket and its resources with a statement like allow restricted administer resource, effect allow, action, 20-something S3 actions, including S3 put replication configuration, S3 put object version ACL, on down through S3 delete policy, S3 delete bucket policy, and S3 bypass governance retention. It applies to resource sensitive app data /star and sensitive app data bucket. The principal, AWS star, condition, ARN equals AWS principal ARN array, ARN AWS IAM 111 user /CI, ARN AWS IAM 111 role admin. Notice the long list of API actions include some that operate on buckets, for example, S3 put object star, and bucket objects, for example, S3 put object star, and somewhere it's not particularly clear what type of resource applies, for example, S3 put metrics configuration. We can create similar statements to allow reading configuration as well as reading or deleting data. The full policy for this example appears in Appendix Least Privilege Bucket Policy. We won't include it here because it's over 200 lines. To adopt this least privilege model for your own bucket, replace the principals and bucket name with your own. Then put the policy into effect by populating the policy contents into the bucket's policy attribute in CloudFormation or Terraform, the AWS CLI, or console. These all invoke S3 put bucket policy. Finally, verify policies can still access data as expected. Resource policies are stored within the scope of the resource and cannot be shared between resources directly. We'll discuss how to scale your approach to implementing least privilege in AWS later in Chapter 5. Let's wrap up our, quote, simple example. This simple example demonstrated a few things. First, wrapping up. This simple example demonstrated a few things. First, the AWS IAM security policy language is flexible and powerful enough to implement fine-grained access controls to AWS API actions and data. The AWS identity and resource policies created in this chapter implement our high-level goals. They allow only authorized principals to access data in the way we intend and enforce encryption in transport and at rest. Second, it wasn't easy or straightforward to implement the policies we needed. The policy language is complex and some effects are difficult to anticipate. I had to close off unexpected access from other principals with excess privileges in the account. Enforcing basic encryption requirements is possible, but took 3 separate statements. And the final policies constitute hundreds of lines instead of a few tens of lines you find in most getting started blog posts and examples. But keep in mind that the access control capabilities provided by the AWS IAM security service and equivalent in other hyperscale clouds have no common analog to on-premises data centers. AWS IAM is over 10 years old, but it is still early, especially when it comes to abstractions that help teams go safely. Keep reading to learn about the problems in AWS IAM and abstractions you need to solve them.